We know that momentum is P equal to mass into velocity. That means momentum is the product of mass and velocity. Then we're going to find a relationship between kinetic energy and momentum. So kinetic energy Ke equals to half mv square. Now you multiply the kinetic energy formula with mass and divide by mass, so that value doesn't change. And if you take the m into m, which is m square and v square divided by 2m. So if you see this, the numerator m square v square can be written as mv whole square by 2m. Hence kinetic energy Ke equal to, we can write it as p square by 2m. So this is very important formula to relate kinetic energy and momentum. Let's do a small problem based on this formula. A body of mass 2 kg, okay, is moving in the forward direction with the velocity v equals to say 0.3 meters per second. Then the question is calculate the momentum of the body. Okay, so the problem in that a body of mass 2 kg moving in forward direction and has kinetic energy 300 joules. Then calculate the momentum of the body. Now we know the formula Ke equal to p square by 2m. Then from that we can rearrange the formula and write it as p square equal to 2m Ke, and hence p equal to root over 2m Ke. So therefore 2 into mass is given 2 kg and kinetic energy is 300 joules. So the answer is 34.6 and the unit of momentum is kg meters per second. So if the mass m is constant, then you can see kinetic energy is directly proportional to momentum square. So what it means? It means when the momentum increases, kinetic energy also increases. For example, if momentum is doubled, then kinetic energy Ke is proportional to p square, so is proportional to 2p whole square is proportional to 4 p square. Then the new kinetic energy Ke dash is proportional to 4 into Ke. That means kinetic energy increased by 4 times. So kinetic energy increases very fast when comparing to the momentum, as momentum square is the kinetic energy. Okay, let's learn the next concept called impulse. It is a vector quantity, is represented by the symbol I. So what is impulse? So let us take the Newton's second law, which is equal to force F equal to delta P by delta T. Then from that we can write delta P equal to F into delta T, and this F into delta T is called impulse. So impulse is defined as product of force and a short time. Or you can also say that force acted in a short interval of time. So where it is used in real life situation? If you observe the fielders in a cricket match, the fielder in the cricket match, when he wants to catch the ball, so what he does, when the ball is coming towards him, he doesn't show the hands, doesn't move the hand upward direction to catch the ball. He just move the hand in backward direction, so that he increases the time of fall of the ball towards him. So that as the time of the fall increases, delta t increases, then what happens to force? Force decreases. Force means the force of impact of the ball on the hand decreases, because from the formula I equal to F into delta t, we get to know that when impulse is constant, then force is inversely proportional to time. So lesser the time, more the force, or more the time, lesser the force. So in this example, when the fielder wants to catch the ball, he moves his hands in the backward direction such that the falling time increases, and hence the force of impact on his hands decreases. So that's how the impulse is useful in real life situation. One example. The second example, you see, there is a big tower, and two situations we discuss here. One is this is a road. It's a hard road. Now, a person standing on the top of the tower and he jumps on the hard road. Obviously, you see that the moment he jumps on the ground, you can see that he gets injured severely. But the same situation, if you take in a different scenario, like here is sand hump. Okay, this is a sand hump where the person on the top of the tower, he jumps on the sand. The moment he jumps on the sand, you can see that the injury is not that much severe compared with the previous case, because when he jumps on the sand, what happens? He slowly goes into the sand. So it doesn't touch the ground directly, but indirectly through the sand touching the ground. So when you're going through the sand, what you're doing, you're increasing the time of fall to the sand. As the time of fall increases, as you know that the force of impact decreases. So that's why the injury is not at all happen in this case, and hence the impulse remains constant. So these two examples tells that when the impulse remains constant, force and the short time are inversely proportional. And this is how you can discuss many examples in real life situations. Okay, so once again, if we see the formula, impulse I equals to force into time. With that formula, we can say that the SI unit of impulse is, you know, that force into time, so it is Newton into second. But of course, you need to remember that impulse is also delta P, which is change in momentum. Change in momentum. That means impulse, another unit, you can express it as a unit of the momentum, which is kg meters per second. So the SI unit of impulse is Newton second, or it can be kg meters per second. Now if we take the graph between the time delta t and the force of impact on the y-axis, okay, and say there is a graph like this, a straight line graph, and the straight line graph tells that as the time increases, the force of impact is constant. Say the graph is started at point F and reaches to point A. Now if I ask you that what is the impulse from this graph, how do you determine the impulse? Determine the impulse. So as we know that impulse is the product of force and time, that means here it is the product of y-axis and x-axis, and product of y-axis x-axis nothing but area under the graph. This area we need to take. So area of FT graph gives the impulse. So in this case, it is F into delta T is the answer. Take another example based on the graph. Suppose we have taken delta T on x-axis, force of impact on y-axis, and another graph is this way, go to A. So So as the time increases, force also increases, and we want to determine the impulse from the graph. And here also same thing, because we need to take always area of the graph, but this time this area of the graph is nothing but the area of f into delta t graph, but it is nothing but area of the triangle. Hence it is half into the base. Say the base time is, say it was OAB, so the base is OB and the height is AB. For example, if I say that the force is given here, it is 10 newtons, force is in newtons, and delta t is say milliseconds, and the time is say it is 0.3 at point B, then half into OB is nothing 0.3 milliseconds, which is 10 to the power minus 3 into the height is nothing but 10 newtons. So if you simplify this, you get the answer. So you get the answer 1.5 into 10 to the power minus 3 Newton second. That means 1.5 milli-Newton second. Okay, check this problem. A ball of mass 3 kg moves with velocity 0.6 meters per second and bounces back at the wall with the same speed of 0.6 meters per second, where we are assuming that there is no energy lost, but in real cases some energy is lost. Calculate impulse, and the second question is force of impact by the wall if the contact time is 0.3 seconds. Right, so when this problem is given to you, generally when we think that impulse means I equal to force into delta t, but here there is no force given to you. So how do you solve this problem? But we need to recall that impulse is not only force into delta t, but it is also change in momentum. So change in momentum is nothing but mass, final momentum, which is mv, initial momentum, which is mu. So in our problem, if you see, this is initial momentum u, so initial velocity u, 0.6 meters per second, and bouncing back with the same velocity, and so this is v. Let's say the final velocity is also 0.6 meters per second, that is v. Okay, now let us write impulse I equal to mass, so the mass into the velocity, which is v, final velocity. So but here final velocity direction, if you see, the final velocity direction v is left hand side, so this velocity direction is opposite to our initial velocity direction. So when we are depending on initial velocity direction, as velocity is opposite, we need to take it as minus v, minus m into the initial velocity, which is u. So the formula is minus mv minus mu. Since v and u both are same, you can write the impulse formula I equal to 2mu, which is negative of. So minus 2 into the mass is 3 and velocity is 0.6. Hence the answer is minus 3.6 Newton second. So in this case, you see the impulse direction is negative. Negative means, so this is the direction negative, because we have taken u as the forward direction and v direction is negative. Hence, as impulse is a vector quantity, so impulse direction is left hand side. So I can write left side. Now the next problem, you need to find the force of impact. See, the contact time is 0.3 seconds. So the moment the ball hits the wall, it doesn't come immediately. If you think in a slow motion view, the ball is going towards the wall. At the moment it hits the wall, it is in contact with the wall for some time and it bounces back. So impulse formula, we know that force into delta t equal to delta p, and delta p value already we got, which is 3.6 Newton second. Of course negative sign is there, but in this calculation we don't take the negative sign. So F equals to 3.6 divided by delta t, and 3.6 divided by delta t is 0.3 seconds. So hence the answer is 12 newtons. So 12 Newton is the force acted by the ball on the ball. See the next case. In this case, the 3 kg ball has thrown with some angle to the ball, and after hitting the ball, it bounces back with a different velocity v. Say the 3 kg ball make an angle theta with the horizontal as shown in the diagram, and here we need to find the impulse. So as you know that impulse, again the change in momentum delta p. So what we do here, we need to see what is the change in velocity, but as the velocity is a vector quantity, here we need to resolve the vectors into components because theta is given here. So if I draw a horizontal line which is parallel to the line already drawn, now you can see, and this is also angle theta, as the theta is here. So this theta, because of theta, you resolve into two components. One is u cos theta and this is u sin theta. Now similarly, if you resolve the velocity v into two components, you get this side. This side is say this is same angle theta. This is the same angle theta. Therefore, this is v sin theta and this is v cos theta. So we resolve into two components, v sin theta, v cos theta. Okay, now the thing is, impulse always is in the direction of left hand side, as previous case also I have mentioned to you. So impulse is towards left side, implies if you see the velocities, one is u cos theta which is right hand side and v cos theta which is left hand side, and when we take the right hand side as our initial direction, reference direction, obviously v cos theta will become opposite direction and hence is a new direction. So then the change in momentum delta p equal to mv minus mu, which is final momentum is initial momentum. So the m into final momentum is mass into final velocity, which is v cos theta. But v cos theta is opposite direction if you take negative sign. So final momentum minus initial momentum, which is m into u cos theta. That's what you need to write. Suppose think that as energy is not lost, for example, energy is not lost. If you take the ideal case like this, then you can say u equal to v. In that situation, delta p equal to minus 2 m u cos theta. So we're taking this form into consideration. Minus 2 into mass is given, which is 3 kg, and the velocity is given 0.8, and into cos theta is 30, so cos 30 degrees, and the answer is, so the answer can be minus 4.16 Newton second. So this is a special case where the velocities are equal, energy is not lost if we consider. If not, you will be given two velocities and you need to solve for the momentum, change in momentum and for the impulse.